Sound is a physical force. In an industrial environment, heavy machinery blasts waves of kinetic energy that physically impact the human eardrum. To measure the impact of this invisible hazard across a work shift, safety professionals use a noise dosimeter. This tool continuously processes sound levels to output specific metrics like dose percentage and a time-weighted average. Relying on the device alone is insufficient. To anticipate hazards before machinery is even installed, or to pass the ASP and CSP exams, you must perform these calculations manually. This requires a shift in logic. Sound pressure operates on a logarithmic scale. Consider two identical machines placed side by side, each generating 80 decibels. Intuition suggests they combine to 160 decibels, but that result is a physical impossibility. At 160 decibels, the atmospheric pressure waves would be strong enough to rupture tissue instantly. For an exam candidate, a linear addition error leads to an automatic failure. In the field, it leads to a failure in regulatory compliance, leaving a workforce unprotected and an organization vulnerable to OSHA citations. We will model a full acoustic environment to prevent these errors. This process tracks how sound attenuates over distance, how multiple sources combine, and how fractional exposures are converted into a legally binding time-weighted average. Mastering these logarithmic transformations separates an amateur guessing at safety protocols from a certified professional who can document OSHA compliance with specific, reproducible math. We begin the model on a conceptual factory floor. As acoustic energy travels from its source, it dissipates. The further the wave spreads, the lower the measured decibel level. Take an industrial shaker as our source. At an operator station 10 feet away, it produces a documented sound level of 103 decibels. We need to determine the noise level at a second workstation 45 feet away. This blueprint maps the hazard. To find the attenuated level of the outer ring, we apply the inverse square logarithmic formula. The new decibel level is the baseline plus 20 times the logarithm of the distance ratio. The order of operations is vital. Divide the original distance by the new distance to get 0.222. The base 10 logarithm of that ratio is negative 0.653. Multiply that by 20 for a result of negative 13.06, then add it to the 103 decibel baseline. At 45 feet, the noise level has dropped to approximately 89.9 decibels. Now, consider a workstation with an existing ambient noise level of 89 decibels. If we add 3 new machines, each contributing 78 decibels of noise, we must calculate the new total. Adding 89 to 3 instances of 78 linearly results in 323 decibels. This number is physically impossible in an open-air environment. In logarithmic addition, if 2 sound sources differ by 10 decibels or more, the quieter source has a negligible impact on the total. The 3 78 decibel machines combine to roughly 82.7 decibels. Adding that to our 89 decibel baseline only increases the total noise level to 90 decibels. Treating acoustic energy as a linear variable results in hazard profiles that simply do not exist in physical reality. To manage these risks, the professional must rely on logarithmic addition. With the environmental levels established, we shift the focus to how these levels interact with human physiology and legal exposure limits. OSHA's Hearing Conservation Program sets the baseline permissible exposure at 90 decibels for a standard 8-hour shift. This graph illustrates the 5 decibel exchange rate. Because sound intensity is logarithmic, every 5 decibel increase in volume halves the allowed exposure time. If 90 decibels is legal for 8 hours, 95 decibels is only legal for 4. While OSHA uses a 5 decibel rate, the ACGIH recommends a stricter 3 decibel exchange rate. You must identify which standard is being requested on an exam, as the results diverge sharply. To find the permissible time for a specific, non-standard noise level, we use the formula 8 divided by 2 to the power of the decibel level minus 90 divided by 5. For a worker in a 100 decibel zone, the exponent becomes 10 divided by 5, or 2. 2 squared is 4. 8 divided by 4 leaves us with exactly 2 hours of permissible exposure time. The exchange rate formula converts raw acoustic intensity into legally enforceable time constraints. Employees move between noise zones all day. They start in a quiet office, spend hours on a manufacturing floor, and finish in a testing cell. To track these moving exposures, we calculate a fractional noise dosage, designated as D. The dosage formula compares C, the actual duration of exposure, against T, the maximum permissible time allowed for that specific decibel level. Suppose a worker spends 3 hours in a 95 decibel zone. We know the permissible limit at 95 decibels is 4 hours. 3 divided by 4 gives us an exposure fraction of 0.75. Later, the worker spends 2 hours in a 105 decibel zone. At 105 decibels, OSHA only permits 1 hour of exposure. 2 actual hours divided by 1 permissible hour gives us a fraction of 2.0. When we sum these fractions, we get 2.75. Multiplying by 100 reveals a total shift dose of 275%. This worker has been exposed to nearly 3 times the legal limit. While the dose percentage clearly identifies the hazard, official record keeping and citations require a single decibel value for the entire shift. We must perform a final logarithmic conversion to turn this dose back into a time-weighted average. The formula multiplies 16.61 by the base 10 logarithm of the dose divided by 100, then adds 90. For a 275% dose, the calculation results in a time-weighted average of 97.3 decibels. This process reverse engineers the software inside a dosimeter, allowing the professional to translate dynamic, shifting exposures into a fixed metric for compliance. We have moved from the raw physics of sound waves to source combination and finally through the cumulative dosage of a moving worker. Once overexposure is confirmed through math, the final step in the safety workflow is mitigation. If engineering controls are not feasible, we apply the noise reduction rating, or NRR, of hearing protection. By subtracting the NRR factor from our 97.3 decibel TWA, we mathematically verify that the residual exposure at the eardrum drops below the 90 decibel limit. Without the preceding TWA calculation, the selection of protective equipment is merely a guess rather than a verified safety control. On exam day, avoid the instinct to use simple addition. Treat every multi-step noise problem as a logarithmic challenge. Mastering these formulas allows you to model physical reality, pass the board exams, and effectively protect the hearing of the people under your care.